pleased to have Jim Buckwalter here. Just remind you about the talks coming up. They're really great talks. I think you're aware there's a lot of new work going on. And there's lots of different structures that people are looking at. So it's really very interesting. Then we have 6 seminars the same day, February 4th. Steve Koonin, as you know, is ran BP's energy division, and he's started and runs this new center in urban informatics, and so that's pretty interesting use of big data for climate change and temperature monitoring and everything. So he's a great speaker. I really encourage you to come. And then David Wood talking about energy proportional computing, obviously for energy efficient data centers and laptops and everything else. And then Walter Cunningham, who's an astronaut, I think it was, does anyone know? I'm forgetting now, which he was in charge of one of the missions. We'll talk about global warming, war, alarmists versus realists. So he's on the other end. So those of you who've heard Philip Warburg speak on Tuesday, he's on the other end of this debate. So we're trying to provide both sides of the debate on this within the Institute. So today, we're happy to have Jim Buckwalter talk, and obviously he's been here a fairly short time, and from UC San Diego, and before that Caltech, and we're excited to hear about 50 gigabit and other sorts of electronic circuits.
Thank you. Sure. Well, I played a little switch on you. I happened to be working on a paper with one of my students that was in review over Christmas break, and I just had to put a lot of this material that we were working on in the paper into today's presentation. So this is the latest stuff from some of my group members. And it really kind of ties together a little bit better between some of the work we've done in looking at how scaled CMOS will help improve energy efficiency in optoelectronic interfaces, and then some proposed schemes that we've looked at for PulseWidth modulation in electrical domain communication, and how that might be interesting in the optoelectronic domain. So it's not nearly as controversial as those other talks, but I hope that it inspires some discussion here today. So a lot of what I'm interested in is how to move data around these large systems, and I don't try to keep myself constrained to microprocessors, but there are other places where data needs to be moved around at very high data rates. For instance, in something like a phased array, a digital beamform. Didn't like that. Okay, yeah, okay. In a phased array digital beamformer, where each of these elements might be might have a high-speed ADC behind it that's operating at many gigabits, many gigasamples per second, and many bits per channel. So there's a lot of places where data has to be moved around across many elements, whether you're talking about a multi-core microprocessor or potentially a 1,000-element phased array in the future. And one thing that's come to the fore has been these heterogeneous integration, where we can use different semiconductor technologies for different purposes, different technologies for digital, for memory, for RF and mixed signal, and for sensors. And so there becomes this need to move high-speed data across multiple chips that may be in multiple different technologies. And one of the things that's most exciting is that this gives an opportunity for things like new approaches like silicon photonics to be the fabric over which that data is moved. I first started working on this about 5-6 years ago. I was working with Oracle down in San Diego when they came to me saying, we have a ring modulator that we've been developing in a 130 nanometer CMOS SOI process, and we'd like to push the data rate as high as possible. We want to just see, how fast can you modulate this this ring. And so we looked at this process, which was very identical to what Luxtera had already developed, and using their ring modulator, which had a bandwidth on the order of 12 to 13 gigahertz at the time. I'd proposed doing something like a very simple inverter driver, where we could modulate the anode and the cathode of that diode across 2 different voltage supplies, a positive supply and a negative supply, which was something we could do because it was an SOI process. But that wasn't enough to get you to 25 gigabits per second. we actually had to do preemphasis where we would overswing the diode on the rising edge to add a little bit of high frequency energy to compensate for the bandwidth dependence on the diode. And so I came up with this kind of simple single stage preemphasis driver where you'd present both the data of the current symbol and the previous symbol at the same time in kind of an ANDing fashion, a logical AND. So we used this to get to investigate 25 gigabit per second circuits, and the transmitter preemphasis comes at a cost. But nonetheless, using the silicon on insulator diode, we would find this trade-off between voltage swing. So either we would have to drive larger voltage swing on the diode, bandwidth where we'd have limited bandwidth of the diode, so we'd have to drive it with more preemphasis, or higher insertion loss, depending on how the diode in this ring modulator was designed. So to make the necessary extinction ratio, we found that we needed to drive at least 2 volts peak-to-peak swing. And one of the big limitations with this 130 nanometer technology ends up being that the voltage supply of the technology has to be large enough to provide that 2-volt swing across the reverse bias diode. But these PN junctions in the ring modulator, they actually have very low capacitance on the order of 28 femtofarads junction capacitance. And this allows us to consider very, very low power consumption drivers when you compare this to what's done for Mach-Zenders and other 40G types of solutions. So this is what we first developed, the 25G driver that we first looked at. We compared the I at 15 gigabits per second and 20 gigabits per second. And when we didn't use compensation, you can see there's a lot of I closure here. 20G is basically already closed, and then 25 would be impossible. Then when we went to the 20 and 25G, we were able to recover the I's almost completely. But this solution didn't come at without cost. The TX power consumption of that driver now is around 200 milliwatts. And so if you look at that power and the data rate that we're transmitting, that's 8 picojoules per bit, which really is close to what, or basically what electrical interconnects can already do. So that wasn't too compelling. When we went and optimized this ring a little bit more, we later published another paper where we removed the preemphasis completely to see how low the power could go. And these later demonstrations showed power consumptions that were closer to 0.7 picojoules per bit. So it was possible to drop by an order of magnitude by getting rid of the preemphasis and redesigning the rings with a little bit of learning curve in there. So the question that came to mind was, where should you invest time if you're designing circuits here? Where do you spend your energy when you look at a future WDM type link where there might be multiple channels with multiple different lasers, and you need electronics to drive the modulator, the ring modulator, as well as electronics for the receiver? How do you divide the energy that you're going to use between the electronics and the photonics? And then what types of technologies are going to help you get lower energy? So I wanted to really understand whether there was a hope that future CMOS technology would make the entire link from laser all the way down to receiver and including ring heating, whether this would actually get to these sub-picojoule per bit targets when we look at the CMOS scaling in the future. So when you look at this total energy that's required to transmit 1 bit, we have to take into account 4 different factors: the laser DC power consumption, the DC driver power consumption, the receiver's power consumption, and of course tuning power that's used to stabilize these rings since they have such high Q. So everything else here I'm going to assume is basically passive. So there's a loss through the link. That loss is going to include the optical modulator loss, the mux loss, and any kind of waveguide losses. And so that doesn't show up here, but that's going to obviously influence how much laser power we require and how much receive power we require. When you look at the sum of all these sources of power in a link, you can basically model it as a power series. There are going to be some things which are constant sources of power. You know, in other words, as you change the bit rate, that power doesn't change at all, right? There are other things which will be linear with power. Linear with bit rate, meaning that as you scale the bit rate up, the power consumption must scale linearly. And then there are other terms which are going to be higher order, x greater than 1. And these x greater than 1 terms are the ones that are most interesting, because when you look at trying to optimize the energy per bit here, the higher that exponent x, the more you get a steep curve for this energy where it's not very robust to changes in either the processing or the losses or some other link parameter. So you'd like to have something that's insensitive, essentially to that minimum. It can be moved around without great changes in how much energy is consumed in the link. So to understand what this function looks like and then the constituent parts of this function, we really need to dig into the circuits and understand how transistor scaling influences these circuits to understand how each of these parameters is going to scale with bit rate. So there's a few questions I want to talk about today. What are the limits of this energy efficiency in terms of the circuits in serial interconnects using photonic ring modulators specifically? So I'm not going to talk about laser modulation. This is just for ring modulators. And then can we define the energy per bit in terms of photonic and electronic device parameters to determine where the problems are? In other words, what I want to know as a circuit designer is, where do I invest time? Do I invest time designing drivers, receivers, heaters? Where are we most limited? And then finally, my experience, and this is one reason I talked about the preemphasis first, my experience is that a lot of channel coding comes at high power consumption, right? I showed you this order of magnitude difference when we use preemphasis than when we got an optimized ring and we could drive it with low power, with much lower power consumption. So are there other forms of channel coding that might help us reduce power consumption? So first, the energy efficiency. And a lot of this is background. I have a lot of equations here, so I'm going to try to make this as painless as possible. The DC laser power consumption is obviously going to depend on the sensitivity of the link, the power, the insertion loss of the optical routing, and the modulator, and then the wall plug efficiency of the laser. So if we want to understand laser power consumption, we have to dig into the sensitivity. And that sensitivity, of course, depends on the pin diode noise, which is something that scales with bandwidth, but also the TIA noise. In other words, the transimpedance amplifier, the electronics that are going to follow this pin diode. So when we want to look at the dependence on bit rate, we can understand the bandwidth to be directly proportional to bit rate. And so we'd like to understand how the bandwidth in the TIA it changes the amount of noise that's generated. So digging into that a little bit, we have to start with the circuit topology. We have to start with one particular circuit, because it's impossible to say what's the input referred noise for any generic electronic receiver. And when we look at very scaled CMOS, when we look at digital processes today, at 28 nanometer and lower, one thing that's really interesting that comes out is the PMOS devices and the NMOS devices are very similar in terms of performance. And it happens to occur because of straining in the channel. So the idea of using what looks like a digital inverter comes to the fore as the best approach for a low power circuit. Because first of all, digital inverters are what these technologies are designed to build and designed to implement. They can be implemented with a small pitch, small area. And so they end up being very area efficient. So we're going to look at this particular type of TIA where there's no inductive tuning techniques to extend the bandwidth, primarily because this is the smallest possible TIA you can make in a microprocessor circuit. And so the way you end up analyzing this circuit is the push-pull amplifier, the inverter, would define a gain based on the transconductance of the transistor and the output conductance of the transistor. And then the input resistance and bandwidth would be defined by the feedback resistor that you're going to stick between the input and the output. So the typical TIA, we want to choose this feedback resistor to make a certain bandwidth at the input so that we can receive a certain bit rate. So as we go to higher bandwidth, this feedback resistor size drops. What does that mean? So what? The feedback resistor drops in size. Well, it turns out you can express the TIA's noise, this term that's going to go into the sensitivity, in terms of this feedback resistor, the transconductance of the transistors, and the photodiode capacitance. So if you have a smaller and smaller feedback resistor, that means this noise is going to go up, right? And so that means it's going to be something that's competing with the pin diode noise. And in fact, this is going to dominate the overall noise. So looking at plugging in this feedback resistor term we just described, we can calculate the TIA's input referred noise in terms of the photodiode. So that's a photodiode capacitance is an optical parameter, or a parameter of the diode that's being made in this process. The intrinsic gain of that inverter, and the transconductance of the transistors. So when we look at this equation, if we're circuit designers, the one thing we can really play with, we won't change the AV very much, but we can change the GM of the inverter. In other words, we can make this width, WP and WN, we can make the inverter bigger and bigger and bigger, right, to get more GM. And what this says is as we do that, the noise gets reduced, right? So we increase GM, we reduce the noise, then we ostensibly need less laser power, right? But that comes at a cost. Increasing GM means that we need more drain current. And drain current means we need more DC power consumption in our receiver. So you can see where I'm going now. Because the laser power consumption is now going to be determined by the TIA power consumption, we can see that there's essentially a minimization that has to happen here. I either increase my laser power consumption to have a higher sensitivity and lower TIA power consumption, or I increase the TIA's power consumption so that I get lower laser power consumption, right? So this whole thing, all this math that I've done so far can be essentially written as that the laser power depends on some constant plus b over the square root of p TIA, the power of the TIA. And what we want to minimize is the sum of that laser power and the TIA power. So it turns out that there's an optimal laser power consumption. And that depends on these optical terms, the loss, the Q of your communication system, the responsivity of the diode, the wall plug efficiency, but then a bunch of things that depend on transistor parameters, the voltage supply of the technology, the overdrive voltage, and then, of course, the photodiode capacitance. So from this optimal laser power, we can go back and find the optimal sensitivity and optimal TIA power. And it turns out when you look at these different things, they scale linearly with bandwidth. This optimal value scales with bandwidth. So when we use parameters that are most similar to what we'd find in a modern CMOS process, what we'd find here is that we need on the order of, at 40 gigabits per second, we need on the order of 0.5 picojoules per bit for the laser and 0.25 picojoules per bit for the TIA. Okay? So already you can see this optimum value for the laser power is totally linear. So this energy efficiency scales. Doesn't really matter what bandwidth we're talking about. This is going to be the optimum. And the same thing is true for the TIA power consumption. But TIA is not the whole receiver, right? So one thing you might say to me is, well, what happens if you consider the receive power consumption? And one insight into that is that as you change the bandwidth now, or as you're changing the bit rate, the TIA sensitivity, of course, changes as well. And so you expect that you can build a much more sensitive receiver at 1 gigahertz bandwidth than at 40 gigahertz bandwidth. But one thing that's very interesting here is that our optimum TIA sensitivity that we calculated is much higher than the shot noise. In other words, we're not really designing TIAs that work down here. And this was an eye-opener for me because, as a circuit designer, I thought, okay, we look at the TIA, let's build the lowest sensitivity TIA I can, right? And what the optimum is saying is you don't design for the lowest sensitivity, you design for this sensitivity, and you try to get the lowest power consumption, all right? So that means that there's actually a sweet spot for TIA design, and just publishing things that are lower and lower sensitivity doesn't necessarily make sense. Now, the other thing to note here is that as the sensitivity gets better, you need more gain to amplify your signal back up and recover it. And so we need post-amplifier stages. In other words, after this TIA, I'm going to add another amplifier stage and another amplifier stage and another amplifier stage. And so it seems like the receive power consumption is going up. But something very interesting happens here. When you look at how many stages are required to amplify a signal to, for instance, the full supply voltage, you get this term that depends on the ratio of VDD over the responsivity P-sense and then the feedback resistor. And what's very interesting is that the only thing in here that depends on bandwidth is the sensitivity and this feedback resistor. And the product of these two things is independent of bandwidth. In other words, you always need the same number of stages in a receiver, whether you're talking about a design at 1 gigahertz or a design at 40 gigahertz. The number of stages doesn't change with bandwidth. And so the receive power consumption is directly proportional to the TIA power consumption. Once you know the optimal TIA power consumption, you're just adding a factor. In other words, this is a scaling factor that is independent of bandwidth to find the overall receive power consumption. Okay? So that was something else I didn't know before we embarked on this exercise either. And I found that very, very eye-opening. I compared this here. This is the same plot I showed you before, where we're showing the optimal laser power as a function of bandwidth, the optimal TIA power, and then for a scaling factor of 1.2 or so, you can see the receive power is higher, of course, than the laser power. And most notably now, if you add up, for instance, at 40 gigahertz, the 20 milliwatts for the laser, the 20 milliwatts for the receive power, you're above the 1 picojoule that you wanted to be at. But there's a third element here, which is the transmitter. And this comes back to our ring modulator. If we want to do the simplest possible driver for these ring modulators, we're again looking at inverters. But these are large signal circuits where we're driving the inverter from ground up to the full swing, and then on the negative side from ground down to a negative bias so that we get the largest voltage swing across the diode. And so it turns out you can look at this as a slew rate problem. If you want a certain rise time and you have a certain modulator capacitance and a certain output capacitance that it consists of the intrinsic capacitances of the transistors, then you need a certain current, right? And so the slower you want this rise time, the faster you want this rise time, the lower you're going to want this the larger you want this drive current. And so we did some analysis on this some time back where we looked at 65 nanometer, for instance, and we found that there's essentially this output capacitance of the driver becomes a problem because as you want more drive current, you make the transistors larger, and they end up requiring a lot of the drain current to drive these capacitance as well as the modulator capacitance. So you can write the overall power consumption for the driver in terms of a CV squared type relationship, which will obviously scale with bandwidth here. But there's this output capacitance, and so when you look at 65 nanometer, for instance, and you start scaling the bandwidth, you can see that the power consumption increases much, much, much more rapidly than when you look at 28 or 14 nanometers, and the power consumption is much, much lower. So in other words, taking the derivatives of these, the self-capacitance of the transistor causes this energy to increase even as you increase the bandwidth, whereas the finer scale technologies are fixed with data rate. So the good thing is scaled CMOS obviously helps you here, but it's helping you basically because the parasitics of the transistors wash away from the problem. So here's a summary of what we learned. The laser power consumption we can write as a term that depends on constant, linear, and 3/2 exponents when you come back to my curve for total power as a function of bit rate. Receive power consumption depending on a cubic term. The transmit power consumption is something that scales with bandwidth. And then the heater power consumption, we did some experiments on this, but for the most part, it's something I'm leaving out of the talk for time constraints today. But this basically is constant. It doesn't really matter whether you're looking to design something at 1 gigabit per second or 40 gigabits per second. The amount of tuning power kind of remains constant because it's a low frequency circuit. So now, with this insight, I want to talk a little bit about different transistor technologies. Okay, so these are the parameters for a photonic link, for a CMOS technology that we can plug in, but we want to know a little bit more about how the transistors scale. And I'm looking at two different types of technologies here. And this landscape has changed a little bit, but one technology is a 28 nanometer FDSOI, which was from ST Micro. And so this is a planar device, a traditional transistor, traditional CMOS transistor. And then a FinFET. We were working with Global Foundries a couple of years ago on this and looking at a FinFET on SOI, which I think is no longer something that they're exploring. But it's a data point to look at. But looking at these two technologies, they have roughly the same supply voltage. One's at 1 volt, the other's at 0.8 volts. The threshold voltages are very similar in terms of ratio of the supply voltage. But one of the big interesting things here to note is that as we scale CMOS now, there are cost aspects to this as well. And when we were looking at the FinFET process, the costs for a university lab to use this were extraordinary. It was like $80,000 a tape out, right? So these were very expensive CMOS processes by modern standards. And you can see this on the cost, this cost scale over here. This is the cost basically per wafer, and you can see that as we've gone from 90 to 65 to 45 to 28, there's been a reduction in cost, and that's generally what people are excited about with Moore's Law. But when you go beyond this to 20 and 14, this flattens out and arguably is going up, okay? So there's a couple reasons. The processes are very expensive, but also the design tools are very expensive. And of course the design time the lead times are much longer. So there are reasons why people don't necessarily want to push all the way to 14 nanometer. And so one of the things I wanted to understand is, was there a sweet spot for these types of circuits as well? Should you be designing them in FinFETs or planar devices? And I think this is a little eye-opening here. When you look at the transistor FT between 28 nanometer FDSOI and 14 nanometer FinFETs, they're very, very similar in terms of the peak speed, the FT of the transistor. The NMOS hits 400 gigahertz, the PMOS down at about 220 for FDSOI. But for the FinFETs, you can see the NMOS is hitting 400, but the PMOS is at 300. So much closer in performance. And so the P-type devices are obviously better in the FinFET technologies. But FT is not the only way to look at a circuit technology. The other thing we would want to look at is a push-pull amplifier. So in this case, we're looking at that intrinsic gain of the inverter. And you can see, for instance, in this case, the FinFET is offering you about 60% higher intrinsic gain than the NMOS, than the traditional planar device. And so based on our predictions, that should be something that's very good. A final thing to consider is the efficiency, the GM efficiency. How much power consumption does it take to get a certain transconductance? And so you want high GM over ID because that means you're getting a lot of gain for a given power consumption. When you look at that type of metric here in the design range of voltages where you would want to bias this inverter, you can see that actually now the FDSOI is a better choice. You can see that it has higher GM per ID than the FinFET technologies. So I've shown you a couple different ways to look at a transistor technology, and I've given you inconclusive results. They're similar FTs. The PMOS devices for the FinFETs are a little bit better, but the intrinsic gain for FinFETs is higher, while the GM efficiency for the planar devices is better. So let's look at plugging these into those optimization equations and see how things scale. First, let's look at the receiver sensitivity. So on this plot, we're going to assume a certain amount of photodiode capacitance out of argument. You know, you can change this, we can completely remake the curves, but we just assume something that was on the conservative side. And then at 25 gigahertz, we looked at we looked at a number of data rates. But at 25 gigahertz, for instance, which is this point here where there's kind of an inflection, the 28 nanometer technology gave us a sensitivity of minus 13 dBm, while the 14 nanometer gave us minus 16 dBm. So it was about 3 dB better. If you go back to our mathematical predictions, it was about minus 19 dBm. So we're 3 dB off from where we were supposed to be. And some of this has to do with whether we're looking at the TIA sensitivity or the overall receiver sensitivity. So now, when we look at the energy efficiency of just the circuits on the left-hand side, including both the TX and the RX in the two different technologies, you can see that there's this obvious benefit for scaling. So it looks like as we go to higher and higher data rates, the energy efficiency is getting better and then flattening out for the receive circuits on the bottom here. and then the transmit circuits on the transmit circuits on the bottom and the receive circuits on the top here. And there's obviously a benefit here when you look at the 28 nanometer technology and the 14 nanometer technology, working at the two black curves for the receive. And you can see the solid line is for the FinFET technology, and we're obviously seeing that the FinFET has essentially a 50% lower power consumption. But when we add the combination of the optical devices, and here I'm showing them separately as a loss versus data rate, we assume that the ring modulator actually has a loss which is scaling with bandwidth. And that's kind of an empirical thing at this point. But when we include that loss that scales with bandwidth, you can see that now the energy efficiency is increasing when we go to higher and higher data rates as we include these losses. And so this is a 10 dB loss plus an 8 dB loss, which is giving us this overall increase in the energy. So putting these two pictures together, and including some heater power, and I'm just assuming something that's fixed, essentially the two technologies show that there's an inflection point here where the transmit receive is kind of optimum around 20 gigabits per second to 25 gigabits per second. And then when we go from the 28 nanometer technology down to the 14 nanometer technology, we're able to reduce the power consumption by about 40% here. So this is the curve with lasers. So this includes those optical losses. This was if we just looked at the circuits alone. And so I think one of the things that I learned doing this experiment was, you know, we trick ourselves in the circuit community into pushing these data rates to higher and higher speeds, right? But it really, the optical losses have a big impact on where your circuit should be designed, at what point on this curve you want to design for. And so one way to look at that is to plot different optical link losses, so 0 dB, 10 dB, 20 dB link losses, and you can see how you go from something where you have these very broad energy minima, where we could design from 15 to 40, and it wouldn't really change the energy that much, to when you include 20 dB of link loss, you see this very dramatic increase in how much power is going to be required, and that you actually want to be designing in this 10 to 20 range. And so, you know, looking at this, it's obvious that you have to start with the photonic devices before you really dedicate yourself to one particular bit rate and circuit design. Now, the other question is, well, how do you get to that picojoule per bit that you wanted to be at if you're given, for instance, a 10 dB link loss, which is very optimistic. And you know, you can also plot laser efficiency to see where you need to be before your total power consumption gets you to an energy efficiency under one picojoule per bit. And you can see getting close to laser efficiencies of 50% is where we really start to see something that might be a picojoule per bit with a 10 dB link loss. And that's including the FinFETs rather than the planar CMOS. So the FinFETs obviously have an advantage, and there's a lot of work that's still going on optimizing FinFETs and whether they're on SOI or on bulk CMOS. So I look forward to seeing how the actual devices play out in the future. But now I'm going to switch gears and talk a little bit about source coding. And this was a project that we pursued in the electrical domain, but I think you'll see how it might be interesting in the optical domain as well. And it's motivated by basically looking at the idea of where's the optimal energy efficiency. When you're starting to talk about picojoules per bit, that's where I think the optics needs to be. Electrical can obviously do things in this range. And so we wanted to look at different ways of doing channel coding so that we might see where we can push electrical from the top. So channel coding that I've already talked about included preemphasis. But there's other approaches that people are really excited about, particularly in the optical domain, which include PAM4. But the big disadvantage of PAM4 from a system perspective is now you need linear receivers. You need to be able to detect different thresholds. This is a PAM4i, so you know if you want to detect this signal versus this signal, you need one threshold versus another threshold versus another threshold. And people have looked at this a lot in the electrical domain. But what I was really interested in is I don't want to have all these linear electronics. I don't want these linear receivers. I'd like to really use simple circuits to get the lowest possible energy. And so I said, what if I could leverage time resolution, the ability to resolve an edge here versus an edge here, right? How close can I push those edges together before I can't resolve them with high reliability? And so there's two types of approaches that are looked at. The conventional one is called PulseWidth Modulation, and you can write a bit rate for PulseWidth Modulation in terms of the number of edges that you're able to stick at the end of a pulse. So here's a picture of traditional PulseWidth Modulation. You have a rising edge, a falling edge, and then there's a bunch of edges that are trailing there, right? And that the number of edges there is this factor M. That's great, but that leaves something on the table, right? It leaves some bit rate on the table. If you want to go a little bit further, you go to double-edged PulseWidth Modulation. That gives you an extra factor of 2 here. And what that means is that your falling edge and your rising edge are changing every interval, right? So you're able to change the timing resolution here, then here, then here. And so your signal kind of wanders. Its falling edge and its rising edge are changing with time. But that gives you an extra factor of 2 in your bit rate. So what does this mean? There's 2 parameters that would go into designing the signal. First of all, a reference pulse width. This is kind of like getting your minimum energy across the channel. You choose a reference pulse width to make sure that you have enough energy at the receiver that you can detect the signal. And then this timing resolution, delta t, and that would be how closely spaced these different falling edges are going to be from one or another. If you look at these 2 parameters, you can calculate bit rate as a function of this m. And one thing you'll notice looking at these functions is that there's obviously an optimum, right? Because in the numerator you have something that's increasing with log of m, but in the denominator you have something that's increasing linear with m, right? So there's obviously a point where this curve is going up, it peaks, and then it starts to go down. Again, you don't want to design 64 levels in your timing resolution. You have to choose a particular set of delta t's and t-refs so that you design for the best possible data rate. And so you can see here, if we use either 80 picoseconds reference period, 80 picoseconds of timing resolution, then we'll be at about 4 levels is the optimum. If we go to 100 picosecond, 200 picosecond PREF and then 26 picoseconds of timing resolution, then you're pushing out to about 8. So one thing we need to understand is it possible to push our timing resolution down to something on the order of 80 to 26 picoseconds? And that would help us get to this 10 gigabit per second or better number. The other thing that's really interesting about this PulseWidth Modulation is that it concentrates power at low frequencies. In other words, what you're doing, because you're simply changing edges on the falling edges, on the rising edges, is you're essentially creating a signal that's like phase noise, right? It's essentially a phase noise, a carrier that you're modulating the edges on, and so it has phase noise. And so when you look at the power spectrum of this randomly modulated PWM signal, you see it concentrates energy at lower frequencies than NRZ. That's really interesting because it means that there are bandwidth-constrained channels where NRZ, the data I would be completely closed, but with your DPWM, you could have enough eye opening that you could receive that signal. Okay, so this is what the DPWM eye would look like, by the way, because you're obviously sending edges every delta t. So if you were to plot a traditional data eye, you would be trying to sample in one of these diamonds in the middle. Okay, but there's a catch here. And the catch is that DPWM now, by modulating both the rising and the falling edges, the signal is no longer synchronous to a digital clock domain, right? Because if you send a lot of zeros, for instance, that means that you're sending information you're transmitting an edge on every TREF edge. So the clock is advancing very quickly relative to a digital domain, right? So DPWM makes a lot of complications in terms of edge timing and then being synchronous in both the digital domain and then in your transmit domain. And so we had to develop a digital to time, time to digital conversion. And when we started looking at this problem, it turned out that a Japanese group about 20 years ago now investigated this. They said, yeah, let's do DPWM and let's have this type of set-reset flip-flop where we'll have a buffer, we'll control the delay through the buffer on the positive edge and on the negative edge. And so the signal goes through this way, we adjust the period, and then it goes through this way, we adjust the period. And so we have this independent ability to control the rising and the falling edge. And we looked at this and we said, this is a terrible idea because you accumulate jitter both on this mux, this mux, and this mux, and this mux. And you're accumulating all this noise on every single electronic circuit you go through. And that tends to be bad because it means our timing resolution is going to be impacted. The other thing is this duty cycle distortion is very bad when you look at having a separate positive and negative path. So this is a problem. And then the third thing is that they never solved the synchronous to asynchronous timing issue. And so that was something that we wanted to look at. So my student, Wei Wang, proposed this solution, which was really elegant. It involved a finite state machine where we essentially bring in two variables. One is the information we want to transmit, which is 3 bits for in 8-ary PWM. And then a programmable P, which lets us change the T-ref. So this is kind of a static digital word, and this is a dynamic digital word. And then we go through this integrator in this finite state machine to basically see whether we can adjust the timing yet, or whether the edge that's currently being transmitted has been transmitted. So the state machine takes care of that, and it's kind of highlighted here. I don't want to go through the details. But as the state machine gets updated, we then change a phase rotator. So instead of going through this chain of muxes and delays, we decided to use a phase rotator that could essentially take a given clock edge and choose one of many phases of that clock edge to insert the timing that we want. And then to get rid of the duty cycle variation, we included a divide by 2. So we do all of this at twice the data rate we want to send. So in other words, we're doing this at 20 gigahertz, and then sending something that's at a much lower frequency. So the phase rotator shown here, I mean, the big limitation with the phase rotator is making sure we have a critical path timing. And so the reason why the Japanese group before did not actually address this synchronous to asynchronous, or they didn't use these kinds of approaches, we realized was because this is very insensitive to critical path timing. Because you're going through these delay elements every cycle, that means that the critical path is quite long. When we use something like a phase rotator now, and we're selecting one of these clock edges, we need very high-speed critical path timing. And so we calculated based on the timing delays of the D flip-flops and the selects, we needed to be at least 3 to 4 delta T's for our T-ref. We can't squeeze one edge after another any shorter than four of our timing resolution units. So this meant we needed to use an advanced CMOS process. It was critical. And so we used 45 nanometer here, but you'd get much better results if you went to 28 nanometer or 14 nanometer. And that's very important for a circuit. You want to have benefits from going to faster and faster processes, right, from CMOS scaling. So this is an approach now that I can show you will leverage future CMOS processes better than other technologies might, or other coding techniques might. So these are some simulations we did of our transmitter. In terms of duty cycle variation, compared to the Japanese group's duty cycle variation, you can see they have much more variation in the duty cycle pulse width variation across cycles than we did. We were basically fixed in our proposed approach here, which is in the gray lines. But down here in the bit error rate, you can see the benefit of our approach, which is in red, compared to the theoretical sensitivity that one would have for a timing resolution of 40 picoseconds. As long as our total jitter is less than 3 picoseconds, we can get 10 to the minus 12 bit error rate. So the circuit penalty that we incurred is much better than what we found for the conventional transmitter. Okay. Now finally, this problem of synchronous, yes?
In terms of going back to that general topic, I understand there's edge jitter when you do this double-sided modulation. But I would think from a clock recovery point of view, the fact that you're keeping it symmetric would mean there's less jitter in terms of clock recovery. That doesn't seem to be true. Why is that?
Okay, so you're saying there's two components of jitter here. There's a deterministic component, which is this duty cycle distortion. And the duty cycle distortion may not be changing from cycle to cycle, right? So you may have different duty cycle distortion on a positive edge than you would have on a negative edge, right? And I think your comment is, does that really matter? If my receiver knows that, can it adjust for it? And the answer is probably it can. And the way we did our receiver, I'll show you in a second, we use different banks to detect positive and negative edges. But when you're looking at overall jitter on an edge, there's two components. There's going to be that duty cycle distortion, which is static, and then random jitter, right? And so you're adding those two sources of jitter up. And so the kind of ambiguity on the edge ends up being a mean value, which is determined by the duty cycle distortion and the random jitter, right? So it's kind of like mean plus variance. So the duty cycle distortion really hurts you if you're trying to get something that's a total jitter of 2 picoseconds or 3 picoseconds. You know, a little bit of duty cycle distortion makes this get much worse. Is that?
Yeah.
Okay.
And then the problem with doing both sides is you sort of can go half the excursion if you just do single-sided.
Yes.
So is that why the one answer was 8 and the other answer was 4, because you lose half that excursion?
No, I think when you look at so you're saying here, why did it end up going from 8 to 4? This just happens because of the math here. There's two.
If you look at that figure up there, you can only go half as far if you pull it in on both sides.
You always transmit a minimum Tref. No matter what, you're always putting Tref between the symbols. So the positive edge may last longer, but when it goes negative, it's going to stay negative for at least a Tref. So we have to enforce that to make sure the circuit has time to figure out what the next edge is going to look like. You don't seem satisfied.
Well, it seems to me that when I start doing the red as well as the blue, if I didn't have the red there, I could have the Tref over to the right, and I get more blue steps on the left-hand side.
So you're saying you could go back to the pulse-width modulation where you'd always have a fixed edge here. Yeah. So pulse-width modulation, you certainly can do that, and then you always will have an interval here which is less than Tref in a pulse-width modulation case. But the reason we didn't want to do pulse-width modulation is it ends up not getting as high a data rate. So there are complications going here, and you could argue that this is a better approach actually if from a system perspective this is going to support clock and data recovery a little bit easier. Does that make sense? No problem. Okay, so now this synchronous plesiochronous timing domain. We have a clock here which is being generated by a digital, say, a microprocessor or something like that. It's happening every period t. And then we have this this transmit domain where we're generating this digital to time signal, this double-edged pulse-width signal where the clock is changing with time. So we needed to come up with this elastic buffer where we could put data into a shift register that cycles around. And the problem is that when you figure out how big this elastic buffer needs to be, it essentially grows with time. If you looked at, for instance, a PRBS signal, this is a 2 to the 31 PRBS signal, you need more than 100 spaces inside of this elastic buffer to make sure you handle a peak excursion between the data you're putting in and the data you're taking out of the elastic buffer. That's no good. It's way too much computational overhead, way too much power. So we needed to use some source coding to enforce run length limits, okay? And that's not something new. We just used 8-bit, 9-bit encoding, and when we do that, we end up bounding the amount of excursion we'll see to about 3 or 4 places, and so that makes this elastic buffer much more simple. And you can see that the 8-bit, 9-bit works very well with our 3-bit scheme. We take an 8-bit word and we can encode that with an extra bit where we just take into account the run length that we've currently reached, and then we can flip the data to make sure that we stay within the run disparity we want. So this is the time to digital converter that okay, so I'm sorry, that's the end of the transmit side. On the receive side, we have a time to digital converter. So we're going to receive an electrical signal here, and then take the positive end and put it into one time to digital converter, take the negative pulse widths, put them into another time to digital converter, and then mux between them as we get results. And for this, we use what we call a digital integration. We look at the positive edges and we sample them with a bunch of high-speed clock phases, right? Again, we have a very high-speed clock here that we can sit there and sample to determine how wide was this pulse, and then calculate the sum through a digital accumulation here. And this is all pretty straightforward to do at 10 to 20 gigahertz. So the measured pulse-width modulation here, we had done this, as I said, in 45 nanometer CMOS SOI. This is a picture of the chip. We did different T-refs for 4, 5, 6, and 7 delta T's. Again, the delta T here is, I think, 40 picoseconds. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yes, about 40. 40 picoseconds, and we measured an RMS timing jitter that was less than 1.3 picoseconds. So the timing jitter measured in the middle of this eye is about 1.3 picoseconds. Again, to be 10 to the minus 12, we predicted we needed to be under 2 to 3 picoseconds. So we measured that this transmitter had essentially an eye opening that was about 31 picoseconds out of the 40 that we originally had for 10 to the minus 12, and an eye opening of 313 millivolts. Receiver bit error rate, basically you can see that with our receiver now, on top of the DPWM, the ideal tolerance was less than 3 picoseconds. In our measurement, we actually saw that we had a tolerance that was about 1.8 picoseconds when we added the receiver. In simulation, we expected to see a tolerance that was closer to 2.5. Now, one of the things I should point out here, these are circuits running at 10 gigabits per second. Our transmit energy for the circuit was about 4.4 picojoules per bit. The receiver was 3.8 picojoules per bit. And that includes all of the clock edge timing circuitry, the elastic buffer. So a lot of the digital CMOS we could throw at this problem was useful for leveraging lower power consumption on the overall system. Scaling to 28 nanometer would, of course, be very useful because we could cut that digital power consumption down. We could potentially get better timing resolution and then get higher data rates while reducing the power, and maybe be in the few picojoule per bit range. So in conclusion, I've done a little work with the silicon photonics, and one of the things that's always stuck out of me as a circuit designer was, you know, what are we really designing the circuits to do? Where should they be? And so I wanted to present this to you as a fundamental link analysis, and maybe somebody's going to come up and say, this is the craziest thing I've ever seen, it's stupid, you're making the wrong assumptions. And if that's true, please do, because the paper's in review. The electronic and photonic devices, I wanted to take those parameters in and basically figure out how to predict where my circuit should be. And then also use this analysis to look at different CMOS technologies and think about, well, should we be designing circuits in 28 nanometer? Should we be designing circuits in 14 nanometer? Because a lot of the memory and the microprocessor design, that's going to go to the most advanced node. And when you're thinking about heterogeneous technologies, the question is, should we be doing this comms inside of the microprocessor, or should we be doing it at in a different place? In terms of what I found, the FinFET technologies tended to have a 60% benefit compared to planar devices. And in terms of with the optical link parameters, the 14 nanometer was closer to 80% better. So I think reaching a picojoule per bit is still a challenging thing, and I'm hoping that I'm proven wrong. This is completely theory, and I'm just looking at the link parameters, but I'm hoping, you know, you really, with the photonic ring modulator, the thing that I've really come to is the loss, the insertion loss of that element is a big problem. And until you can get losses that are, insertion losses that are under 8 or so dB, it seems very hard to get that picojoule per bit. And so finally, it was a little disconnected, but I think you'll appreciate it. We presented this new time domain encoding techniques that we've proposed, where we can essentially look at using timing resolution on the kind of tens of picojoules, tens of picoseconds to reach more than 10 gigabit per second transmission. And then we used an advanced CMOS process to show that the whole system there could consume under 10 picojoules per bit of energy. So with that, I want to thank, of course, the students that worked on this work, Wei Wang, Jun Li, amongst the others that were taken in this picture. This work was supported by NSF and Oracle, and most of our circuits were taped out through the Trusted Access Program Office. So any questions? I can probably take a few. I've got to go to teach a class at 5 o'clock, so that's why I'm kind of rushing here at the end. So thank you for sticking through it with me. I'll take a question or two, and then I'll probably have to run.
One quick question.
Can we ever get to 50 gigabytes? 50 gigabits per second. All your diagrams is 25 before you went to pulse position.
We can do 50. I just don't think it's going to be the most energy efficient.
But you need to go high in bit rates.
But what I'm saying is the electronics power consumption scales faster than that bit rate improvement. So if you say that the losses are going to be much lower from the optical domain when you go to 50, I think maybe there's an argument. But in terms of looking at these photonic ring modulators, I don't see a benefit to go to 50 yet. But you know, I obviously think the electronics, I can build the electronics that go to 50. We've built 50 gigasample per second track and holds. I was going to present that today, but I thought this was a little more interesting. So we can do the 50. It's just not clear to me that if you're working from a ring modulator-based link, that's going to be where the minimum energy is.
All right. Thank you.
Okay.
One last announcement. So Roger helped me stand up Roger, the new associate director for the Super Energy Efficiency and the American Institute for Manufacturing. So welcome. Roger is the former VP of Engineering at Italian Networks and built it up to quite a nice size and something like 150 people now. So so welcome. Glad to have you. And he's a graduate of UCSB as well as Caltech. So very illustrious advisor. Yeah, all right.